All right, we want the first derivative information for this. So we're going to drive it. And this is definitely one that's hard. Like, thinking about what this looks like graphically is a little tougher. But I'm going to show you what you could do at the end to kind of think about why it should look the way it looks, okay? But anyway, if you drive this, you get 6/5 x to the 1/5 minus, not there because 6/5 minus 1 is positive 1/5. Okay, yeah, it's positive, so that exponent stays up in that numerator, right? And when you drive this 1/5 and the 6 here, you get 6/5. But now when you take 1 away, like x to the 1/5 becomes x to the negative. Come on, pen, I need a new battery. 4/5, which means down here, yep. And now right here is where a lot of kids went awry. They didn't know how to handle this, but like I told you, if you derive something and you get a plus or minus between things and one of them's a fraction, get a common denominator. That's going to make this easier, okay? My common denominator, look, this has a 5, this has a 5 already. So the only thing I need to do is put an x to the 4/5 right here, okay? So keep in mind, this is really, this thing over here is 6x to the 1/5 over 5, and this is really 6 over 5 x to the 4/5. So all I'm going to do over here to get what I want is multiply it by x to the 4/5 over x to the 4/5. Yeah, a lot of students doing all kinds of weird math here. All right, that's it. That's how you get a common denominator, right? You multiply the stuff that's not there in there on top and bottom. So look, x to the 1/5 times x to the 4/5 is what? It's not squared. You add them. What's 1/5 plus 4/5? It's 1. It's just 6x minus 6 over the common denominator. No, there's not 2 x's. There's an x to the 1/5, and there's an x to the 4/5. Yeah, man, look. So I find that, yeah, kids let things mess with them when they're weird. What's x squared times x to the 4th? Yeah, it's not x squared, it's 2 x's. You add the exponents. Okay? If it was x to the 1/2 times x to the 1/4, well, now I got to think of this as x to the 2/4 times x to the 1/4. That's x to the 3/4. You just add those exponents up, okay? But now I have a nice easy fraction that I want to equal 0, or be undefined technically, right? So I don't even like writing equals 0 there. We're going to look at where the numerator is 0, and we're going to look at where the denominator is 0, okay? That's what we need to know. This here is really going to make it undefined, though. If the denominator is 0, then it's undefined, but that's okay. Cool? If, like, I'm setting the denominator equal to 0, right? That's really making the whole derivative undefined. If the denominator is 0, then that thing's undefined. That's what we want. Where's it 0? Where's it undefined? Okay? This is going to happen. Look, take out a 6. That happens when x is 1. So that's going to my number line. Positive 1. And this says x. So this is something still kids like freak out about, I think. We need x to the 4/5 to be 0. That means we need a number that we raise to the 4/5 to be 0. The only number that we raise to a power to get back 0 is 0. Yo, if a number to a power, if I told you x squared was 0, what's x? That's it. If I told you x to the 3/2 was 0, what's x? Great. If I said x to the 13/20 was 0, what's x? Always. Doesn't matter what the exponent is. If x to a power is 0, x has to be 0. Okay? If you don't like that, all you're really doing here is raising the other side to the reciprocal exponent, right? To get rid of a 4/5 power, you raise it to the 5/4 power. Okay? Because they cancel, right? Because look, if we raised x to the 4/5 to the 5/4, what do you do when you have an exponent to an exponent? You add them. You add them when you're multiplying bases. When you have a power to another power, you multiply. What's 4/5 times 5/4? 20 over 20, which is just 1. That's x to the first power. That's why that cancels it out. That equals 0 to the 5/4, which is 0. Okay? But, I mean, ideally, you just know the answer there is 0 when you see that. But there's two numbers, 1 and 0, that are going on my number line. So, my f prime number line has 0 and 1. Okay? If we plug in a negative number, like -2, let's do this together. If I plug in -2, which is back here, I'm going to get 6 times -2 minus 6. So all that matters is that's a negative number. Over 5 times -2 to the 4/5. Well, that says raise it to the 4th power and then take the 5th root. What's going to happen to a negative number if I raise it to the 4th power? It's positive. So this is a negative over a positive, which means on this interval, negative decreasing. Okay? Also, 0 came, like the reason why you have 0 on our number line here is because of this piece right here. Because that piece right there is raised to the 4 over 5, that's a quadruple root. We're raising it to the 4th power. And I told you, anytime you get a 0 from something that's raised to an even power, that's called like a double root or a 4th root in this case. Well, what does a graph do at a double root or a 4th root when it hits it? It bounces. So I should expect this next interval to be negative. Because it was negative on the one side. If it bounces off, it's still going to be negative. Okay? But you can plug a half in. If you plug in a half, you get 6 times a half. That's 3 minus 6 over 5 times a half. It doesn't even matter. It's like anything to the 4/5 is a positive number. So that's a negative over positive. Negative again, which is what we expect to happen. 1 was not a double root. 1 came from the 6x minus 6. That's not being squared or anything. So I expect it to change sign. If you plug in a big number like 10, you get positives. Cool? So we have, let's make sure we get this. We have a decreasing from -infinity to 0, union with 0 to 1. You can't just go -infinity to 1. You got to skip over 0. Okay? We have it increasing from 1 to infinity. We have no relative maximums. Okay? Because our first derivative never changes from positive to negative, yes. There is a relative minimum when x is 1, and we've got to find the y value, plug in 1. And this is something that blew my mind here. If we plug 1 into this function, we get 1 to the 6/5 power minus 6 times 1 to the 1/5. What's 1 to any power? 1. So 1 to the 6/5 is 1. Minus 6 times 1 to the 1/5 is 1. That's 1 minus 6. -5. Okay, and that's what the answer to that looks like. Okay. Let me go back here for a second too. So let's talk about x to the 6/5 minus 6x to the 1/5. Again, we can kind of think about what this graph looks like. I know kids don't like to do it because it's kind of like it's not like nailed down completely. But again, 4 things: x-intercepts, y-intercepts, vertical asymptotes, and behavior. Okay? So something we can do here to make this easier is factor it. Factoring usually makes things look easier. If we take out an x to the 1/5, that x to the 6/5, if we take 1/5 away from it, that becomes x to the 5/5. That's just x to the 1st. Okay, now this isn't a derivative, this is y. What makes y 0? What makes, remember, we're multiplying here. What makes x minus 6 0? 6. What makes x to the 1/5 0? 0. This thing has a 0 here and here. Great, well, I don't want to label all this junk. Just out here it's 6. Okay. Make sense? Neither one of them is a double root. Okay? Because look, the first x is raised to the 1st power. Okay? The 5th root doesn't matter. It's the exponent that tells you it's a double root or not, like the numerator. So the 1st power is not a double root, and x minus 6 is not a double root. Okay? So think about this. As x gets bigger, what's x to the 1/5 going to do? No. You're taking the 1/5 power, but if you plug in 100 to the 1/5, and then 1,000 to the 1/5, and then 1,000,000, yeah, this is going to get big. What's x minus 6 going to do? 100 minus 6, a million minus 6. Big. What's this going to do? If I plug in huge numbers, it keeps getting, it goes up here. That's it. That's all it tells us. If I plug in a big negative number, like negative 100, if I take the fifth root of negative 100, can I take a fifth root of a negative number? You can take odd roots of negatives. You can't take even roots. You can't take a square root of a negative, but you can take a fifth root. So if you plug in a big negative number into here, this is going to be a big negative number. Okay? If you plug in a huge negative number into here, like negative a million minus 6, that's a big, now we're multiplying these though, not subtracting. What's a big negative times a big negative? Big positive. So this graph on this side is going to be going up. That's what I know. So right away, look, I know this graph should be decreasing on the left and increasing on the right. Look at my number line. Negative on the left, positive on the right. All right, bye, Louise. Yes, ma'am. Okay, sound good? I know it has to come down here and go through this point, but because it's not a double root, it has to go through it. Okay? Now, because it's a 1/5 power, it's going to look a little weird when it does it. You don't even really have to factor this in, but this thing's going to go like this. It's going to go weirdly like that. That's what a 1/5 root does. Like if you know what x to the 1/3 looks like, it kind of curls through 0. Okay? But then it also has to go through here, and there's nothing special about that point. It's just going to do this. So our graph should decrease until somewhere right in here. I don't know where that is. Okay? Actually, my number line, it tells me it was what? 1. It decreases until 1. Sound good?